All right, so today we're going to discuss more about this Schrödinger equation. Okay, let me just first of all write down this Schrödinger equation. It is actually I h bar partial t of a wave function as a function of position and time. Okay, that equals to minus h bar squared over 2m and d squared over dx squared psi xt, and then plus a potential, okay, as a function of position. Okay, so this is the Schrödinger equation, okay. Right. Of course, this is a fundamental postulate of quantum mechanics. So that means cannot be derived, okay, or proved mathematically, okay. So you can only check, can only be checked against the reality or experiments. Okay, and it actually has been checked to be correct by numerous experiments. Okay. But they, of course, you can say that there could be some motivation to come up with this this form. Okay, it's not a proof. Okay, but they give us some kind of understanding. Okay, so if we remember that when we have the de Broglie matter wave, we know that there's a writing of the energy that is E square, right, minus momentum squared and p to the power squared equals to m0 squared c to the power 4, right? Or let's say just use m. Okay, the m is the rest of mass. Okay. So this is the relativistic energy dispersion. Okay, and then we know that this one can be written as h bar omega squared. Okay, minus h bar squared k squared c squared, that equals to m squared c to the power 4, right? So this is by de Broglie's idea, so you can get this one. Okay, just say that the energy is given by h bar times the frequency, angular frequency, and momentum is h bar times the the wave factor. Okay, and then if we do this to the long relativistic limit, okay, so you can say that this h bar omega is going to be the square root of mc to the power 4 plus h bar squared k squared and c squared, right? And then do a tight expansion. Okay, so this will be about mc squared plus 1 over 2m and then h bar squared k squared, right? And of course, approximately. Okay. Right, so you should have this kind of dispersion, okay? And so that means, so this one, if we write down a plane wave, okay, you can say that it's a solution of I partial t. Okay, so you suppose you have this one psi xt equal to this one. that will equals to, minus h bar squared. There's h bar right here, okay, because there's omega, there's h bar right here, okay, over 2m and d squared over, so partial squared, let's say, partial x squared and percent xt. Right. So if we compare this one, so this is just a term right here, and this one is a term right here, okay. So this one is give us the kinetic energy, right? And then you can say that maybe it's natural just for us to just add the potential energy. Okay. So that will give us another term. Right. So this will give us the time-dependent Schrödinger equation. Okay. Okay. So this is a time-dependent Schrödinger equation. Right. So of course this is not derived. Okay. This is not derivation, but it gives us kind of understanding of how we can go from de Broglie's idea to guess this postulate in quantum mechanics, and then check this one with experiments and see if this is correct or not. Of course, at this time we can say confidently that this equation has been tested many times. Okay, to probably the best precision that you can have in physics. Okay, and no conflicts has ever been discovered. Okay. All right. So that is the equation. Okay. So this percent xt actually, we have said that it's probability amplitude, right? Okay, it's a wave function of possibilities. Okay, it's a wave of possibilities. That's a Boyle's interpretation. Okay, and then it just has some properties. Okay, first of all, okay, you should have this one to be. We said that this should be single valued. Okay, in X or K space. Of course, here we only consider at this moment we consider X space, but there's one thing I should note at this moment. Okay, except for spin. Okay, and this is not defined in coordinate space. Okay. The spin is kind of internal degrees of freedom, so it's not defined in the gas X space. But we're going to discuss this one later. Okay, not right this moment. Okay. Secondly, this one should be continuous. And actually, at this point, with the Schrödinger equation, we can actually say a little bit more of this one. So actually, even d over dx is continuous if the potential V is not infinite. Okay, let me show you this. Okay. Because you look at this equation, look at this. So this equation can be written as something like this one, right? Okay. So look at this one. So this is the differential of the wave function. So if we do the integration, okay, from, for example, x minus a very small number to x plus a small number. Okay. Right. So you can see the left hand side is going to be okay. And the right hand side is going to be, you're going to have two terms, right? So the second term can be, the first one can be actually integrated because this is a differential derivative with respect to x, right? And then you have another term. Okay. But you can see that this one is less than infinite. And this one is also less than infinite. Okay. So that means, so if eta goes to 0, so you can say that and this one goes to 0. So that means the first order derivative of this one is continuous. Okay. So you can see that if the potential is finite, okay, you can actually have not only the wave function is continuous, but also its derivative is also continuous. So this one will be useful. Okay, later for solving the equation. Okay. So keep this in mind. So later we're going to use this. Yeah. And of course, there is another property of this wave function. That is, in principle, so this one should be, all right? That means should be normalized. Okay. And there are a few notes. Okay. That we should mention. Okay. You know, per se x t, you can times any number. Sorry, is the same as this wave function. Okay, after normalization. So this is what we have learned before. So if you look at the wave function, and then you multiply arbitrary constant or complex number to this wave function, you know, it may change this wave function, you know, as a wall factor, but it does not change the physics. Okay, because if you calculate any like the distribution of position or distribution of momentum, that will give you the same results. Okay, because anyway you need to do the normalization. Okay. And note 2, you know that this one, actually, this is a plane wave. Okay. It's not normalized. And you cannot multiply any constant to this one, you know, to make this one to be normalized, because this just equals to infinite. Okay. So that means this kind of wave function cannot be normalized. Okay. So in this case, so we should actually consider a wave packet. Okay. Okay. So instead of consider a single state, a single plane wave, you physically Okay. We needed to consider a superposition of many of these kinds of plane waves to make a physical state. Okay. Okay. And this one can be. This one is now is normalizable. Okay. But we have seen, for example, Gaussian wave packet. You can always follow Gaussian wave packet using the plane waves, and that Gaussian wave packet, of course, after integration is a finite number, so you can form a normalized wave packet. Okay, so that's the note I should add. Okay. Okay. And let me okay, recap this Schrodinger equation again, okay? And then I would use another language, slightly different language. Now I can write down this one like this way. There's also a difference between these two. So if we compare the original one, I say we have two terms. The right-hand side was written as two terms. Right. So this is one term, and this is another term. Okay. So both of these are easily understood. So this is a function. This is another function. You multiply the function times the function. This is okay. And this one is a function. And then you do the differential of this one. It's still a function, right? And then you do the summation of the two functions. So everything just well defined. So, okay, it's easily to understood. But now we take these two, put these two together, as if these two are two numbers. So that's something slightly strange, right? So this one, in mathematics, so this one is called an operator. Okay. So what means operator? Okay. So operator actually is kind of operation. Okay. And so you can say that. So you to understand this, what is operator? You can say that function. You change a number to another number. Right. For example, x to sin x. Right. Okay. And the operator so a function will change to another function. Okay. For example, you have f equals to x squared. Okay. Let's look at this d over dx f. So this is an operator acting on the function that will equals to d over dx and x squared that equals to 2x. So this is a new function. Okay. So you can say that this d over dx is operation that change f equals to x squared to a new function that's g equals to 2x, right? So this is so the operator is basically a way or an operation that change one function to another one. Okay. Of course, maybe you can say that you can have, for example, super operators. That change the operator to another operator, okay. Okay, but that's something that we're not going to touch at this moment. But anyway, in mathematics, a function actually is an operation that changes one number to another number. And the operator is also a function. It's a special function. But the input is a function, output is another function. Okay. For the super operator, the infinite operator ultimately is also another operator by level man. Okay. Let's look at some examples so that we can have more feeling of this. Okay. For example, and this one, we call this one as an operator. The operation is operator X. It's a multiplication. So multiplying X to a function. So that means X multiply a function that will give you X times fx. Very simple, right? So this is very easy. So I put a little hat right here. As indication, okay. Okay. Right. And then you can say another operator. Okay. Right. So you can have d over dx and fx. So that equals to the differential of this one, right? So this is another operator, okay? You can have, for example, you can have x squared. We define this as x times x. So that means if you have x squared multiplied on a function, so that equals to x do this one twice. So that equals to, you do this one first. You got a one function, right? So that is x and x times f. And then you continue this way. So this is also a function, right? And then this function under this operation is another multiplication of it. So that is x squared. And then easily you can say, I can generate this one to say, for example, cubic f that will equals to x cubic times f, right? So you can keep it this way. Right? For example, you can have x squared x to n's power on this f, so that equals to this xm times f. Right? So this gives us a kind of generalization of this one. Okay. So in general, you can say that you can have two operators. You have operator A and the B. Okay, this one acting on f actually is defined as you first acting this right one. Put these two together. You got a new function, right? And then you do this, okay? And of course, you can say that this one can be easily generalized. You can say that for A, B, C operator. This is going to be equals to A, B, and C, F. That equals to A, B, C, F, right? And so you can say that then you easily you have this kind of combination form. That will equals to. So all of this are very intuitive, right? Okay. So you don't need to worry about too much of this one. So it's just as if we are doing something very normal, okay? Like the products have before, okay? But let's look at some more examples. And look at the Schrodinger equation, okay? So in the time-dependent Schrodinger equation, we have Vx. Vx, for example, that can be equals to k x squared over 2, for example, right? Okay. And then if you acting this one on a wave function, so this one can be written as, say, an operator. But this operator, of course, is given by kx squared over 2, right? So this is just one case. And then you said, how about if I have something like this one? So if I have ak times x to the power 4th, and then ak prime over 2 to x squared. How about this one? Okay, and this one gives us another thing about the operation of two operators and do the summation. So this one acting function actually is given by, you do this one separately. Okay, so that's the definition of the summation of two operators. Okay, so then, so you can have say, so that way equals to Vx can be written as this one. So then you have two operators. Right. So all of this one are still very normal, right? Okay. Right. So then you can say that this one so this is an operator. Because this one just take the differential of this wave function twice, and then this is another operator. You put these two together, okay? So that means you do this one as first of all separately, and then do the summation of them. Okay, so that is how we define this one. Okay, and this one, so it's a new operator. So this one is an operator. Okay, because it's a summation of operators. So we call this operator the Hamiltonian. Okay. Right. So this is the Hamiltonian. Okay. And there's another interesting operator, momentum. So this one is defined as h of I d over dx. Okay. Let's check this one. Okay. For example, if we put this one acting on a wave function, so that equals to h of I and d over dx and plus x, right? Very fine. Let's do this one twice. Okay, according to the definition of the square of this operator, so you do this one, you first do this one, right? So that equals to h bar over I d over dx and plus x. So this is a new wave function. It's just a differential of the original wave function, right? And so this one, as we said, is just this h bar over 2 over I times d over dx. So you do this one twice. Do this one again, okay? Right. So that means you're going to have something minus h bar d squared over dx squared and the percent, right? So if we compare this one to the term that we have in the Hamiltonian, in the Schrödinger equation, okay? So you can see that minus h bar squared over 2m and the d squared over dx squared now can be written as h of I d over dx, okay? H of I d over dx and 1 over 2m, okay? So that means this one equals to 1 over 2m p and the p operator, okay? Right, so if we take this one as an operator squared, So you can see that that will give us simply just equals to minus h bar squared over 2m d squared over dx squared and percent, right? So this means, so the Schrodinger equation now can be written as I h bar partial t percent equals to, this is one operator, and this is another operator, right? Or equals to, we call this one a single operator h Hamiltonian, okay? That's the p operator squared over 2m plus this vx operator, okay? So right, so this is the operators in quantum mechanics, right? So now we can do the summary. Okay, so you have x over percent, just x times percent, okay? And x squared times percent just equals to x squared times percent. Very simple, right? And you have any function of this one percent just equal to vx times percent, okay? Of course, let me be explicit that this x is a function of x, percent is a function of x. Right. So this is for the position operator. And they can say that if I have p, let's say momentum along the x direction, so this one should be defined as h bar over I, d over dx. Okay, so that means px percent x, y, z, if it's in the 3-dimensional space, that equals to h bar over I partial x percent. Okay, and px squared percent x, y, z, that equals to h bar over I squared and partial x squared and percent, right? Of course, if you want, you can go to higher orders, but usually for us, a second order will be sufficient, okay? And similarly for py, okay, can be written as h bar over I partial y, and pz can be written as h bar over I partial z, okay? Right? And Hamiltonian, we know that this one has a kinetic energy. We call this one kinetic energy operator plus the potential energy operator, okay? So this can be actually written as p squared over 2m plus v as function of this operator, x. Right, so this is the, and then the time-dependent Schrodinger equation now can be written as I h bar partial t percent equals to h over percent. So this is a very compact form, okay? It's a little bit abstract, but it's perfectly compact. Right, very nice properties, okay? Formalism, okay? Right, and now let me talk a little bit more properties of operators, okay? And we are interested in the linear operators, actually. So what means linear? Okay, so linear means that if I have a function c times percent, and then acting on this one should equal to c, times the operation of this wave function, okay, for any c being a complex number, okay. So this is one condition. And secondly, the condition is that if you have two wave functions, okay, you have a superposition. So this one can be expanded like a So I should write this in a more compact form, okay? So if you have two-way functions, a linear combination of two-way functions, this one can be done just separately. Right, so this is a definition of a linear operator. So you can see that this is a very intuitive definition, right? So you can obviously you can check whether the operators we have defined at this moment are linear or not. Okay, let's check the. For example, you have x. Okay, if you have x times a constant times this wave function, so therefore of course is x times c times percent, and this one of course is x c percent. That equals to c x percent. That equals to c x percent, right? Okay, so this one is a check. Now how about this? The second criteria. Okay, and this one you can say that. So it's x times percent 1 plus percent 2, right? That of course is x times percent 1 plus x times percent 2. That equals to x times percent 1 plus x times percent 2, right? Okay, so this one is checked. So x is okay. Okay, and I let you to check x squared. Okay, should be also be okay. And any function of this one should be okay. Okay, right? So let's check the momentum operator. Okay. And the momentum operator, let's look at the first condition. So this one is h bar of I, d over dx, and c and percent. And this is a constant, right? So it can be moved outside. So that equals to c times h bar of I, right? So quickly you know that this one is correct. Okay, so the first condition is correct. And then of course, it's very easy that you have a differential of the summation of two wave functions. It's just do the differential of them separate and do a summation, right? Okay, so this one is okay, right? So this is okay, this is okay. Sorry, this is okay. Okay, and you can also check that this one. It's also okay. Of course, the Hamiltonian that equals to p squared over 2m and plus vx is also okay. Okay, so they are all linear operators. Okay, and you may wonder, are there any operators which are not linear? Okay, let me give you a few counter examples. Okay. Operators not linear. Okay. For example, let me define the operator, say m, acting on percent. I define this one as just to take the modulus. Okay. So this one basically is and obviously you can say that if we times, for example, ei pi over 4 and percent. This one does not equal to ei, right? So it's not a linear, okay? So you take a modulus of this one, it's not linear, okay? And also you have, if you have two, in general, you have a percent 1 and percent 2, should not equal to percent 1 plus percent 2, right? So that means it does not satisfy either of the conditions, okay? So let me give you another interesting example. I call this one C, for example. C is nothing but just takes the compass conjugate. That's even simpler, right? This looks like more like this one could be linear, right? But it's not actually. If we look at this one, yeah, this one is okay, right? So that actually equals to. So this one is okay. So the second condition is satisfied. But however, if we times any compass number on per side, right, alpha, and this one will equals to alpha psi complex conjugate, that equals to alpha psi and psi star equals to alpha complex conjugate times C psi. So see, this is not alpha times C acting on psi. So that means it's not linear, okay? But this one satisfies the second condition, but not the first condition. This one actually is not linear, of course, but it has other name called antilinear, okay? It's almost linear, right? Okay. This is an operator that actually we are going to use in the future, okay? Not in this course. If you take quantum mechanics 2, for example, we're going to introduce this operator again, okay? But you can see that in general, the operators can be linear or nonlinear, okay? But in quantum mechanics, most operators we use, like momentum, like position, like Hamiltonian, okay? We have introduced. They are all linear operators, okay? So X and P, Hamiltonian, okay? They are all linear operators. Okay. Right. Okay, so let's take a break and let me see if you have questions, okay? Okay, so let's continue. Right, more on the operators. Right. Let me just summarize a few things that we are kind of familiar already with the usual, operation or product, right? For example, we have seen that if you have A plus B, if you have a summation of two operators, this is so easy, right? It's very intuitive. Okay, right? So basically, it's just like A plus B on psi just equals to A psi plus B psi. Right. So this is very intuitive. And also we have something like a linear. And it's also very intuitive. Okay. Okay. So this is also intuitive. That means you don't need to pay too much attention on this one. Okay. And another one is that if you have, for example, a product of this one, so this actually means you do this one first, and then do this one later. Okay. And then from this one, you can immediately say that if you have A, B acting on C, actually can be written as you do this one just one by one, right? Okay, so that simply just write this as A, B, C, because you just act in C first and then B and then A, right? Okay, so that means this A, B, C acting on this psi just equals to you act in C first, and then act in B in later, and then act in A at the end. Okay, so this is also very intuitive. Okay. Right. But now let's take something not that intuitive. Okay. They are operators. There are a lot of numbers. Okay. This is the operator. Anyway. Okay. Not the number. A usual number, right? Even though in some cases, for example, even though this x psi x equals to x times psi, okay, they are just like a number, okay, looks like a number. but it's an operation, okay? So you should be careful with this one. And to show this one, so we can show that, so in general, for example, there's an important counterintuitive thing, okay? In general, so you acting B on percent first, and then acting A, that's not equals to, you acting A first, and then you acting B, right? So this is different from the number, okay? So that means A, B, that's not equal to BA. Okay, so this is something very counterintuitive. Right? It's so abstract. Let us consider a simple example. Let's consider X and P first, right? Let me put this one on a wave function. We know that this means you acting P on this momentum on this momentum operator on this wave function first, and then the position operator. Okay, so this one first, and then this one. So that equals to h bar over I d over dx. Right? That's pretty good. And then this one is a function now. And the x acting on this one is just multiply x. So that's x h bar over I percent prime, right? It's a differential of this. So that equals to h bar over I x times percent prime. Let's check another thing. Let's exchange the order, see what will happen. Okay. So this one again, you activate this one first. Okay. That equals to P and x times percent, right? So that equals to h bar over I d over dx and x and percent. And now this is a product of two functions, and do a differential. You should do this one, by parts. So the first one is h bar over I and the percent, and then plus h bar over I and x times percent prime, right? So if you compare the two, this one equal to this one, but now you have another term. You have an extra term. Okay. So this means xp that's not equal to px, right? If you activate these two operators in different orders on a function, you actually get different results. So this is a very important thing about the operators in quantum mechanics. Okay. And so this is something important. Okay. Right. And to quantify, okay. So in this case, if we say that so if AB that's not equal to BA, okay, we say that they do not commute. Okay. And to quantify how, okay, or how much they do not commute. So we can calculate we define a new operator as AB minus BA. Okay. And this one is called the commutator. Okay. This name is called okay. It's a commutator. Okay. So if this one is 0, okay, that means AB equals to BA. Okay, they commute. Right. So that's the important thing about these operators in quantum mechanics. Let's look at the example for X and the P, right? Again. We had these results. Right. And then we have for PX, they have this term, okay? But it also has an extra term. Okay? So that means if we have XP per se minus PX per se, so these two terms will be cancelled. So you're going to be left with minus h by fi times per se, right? So in this sense, we say that the xp minus px acting per se equals to I times h by per se. Okay? So just because this p has a derivative on x, okay? So you can have, if you put a p on the right hand side, it does not act on x. But if you put p on the left hand side, it's going to act on x. So you got an extra term, okay? So this means the commutator of this one okay, this is the fundamental commutator in quantum mechanics. Okay, according to Dirac in his thesis, okay, in 1925. That means actually using this one, you can derive the whole quantum mechanics, okay, except for, of course, measurement. Because the measurement is kind of interpretation, okay? But otherwise, everything in quantum mechanics can be derived from this one. Okay? So that means from Schrodinger equation, actually, so we can say that from Schrodinger equation, we kind of derive this one, right? So now sorry. Okay. From Schrodinger equation, so to the operators, okay. So this one become the operators in differential equation, okay. And in the differential equations, you know that everything can be written as either a combination of x or a combination of differential, right? So that means you can use x or p to form any operators, right? Okay. So, and then that means this commutator will dedicate all kinds of differential equations, right? In quantum mechanics. Okay. So you can see that there is kind of a reconciliation of Dirac and the Schrodinger, right? Okay. All right. Okay. So now before I move to the time independent Schrodinger equation. Let me just discuss another thing about this wave function. Okay, have a kind of a break. We know that in quantum mechanics, you should have this one equals to 1, right? Okay. And then you should say that so we must have the time dependent of this one. This one should always be 1, right? So that means percent xt, sorry, and percent xt. You do the differential of this one, do the integration of this one, this should be always 1, because the probability should be conserved, right? So this is probably the most robust conservation law you should have in nature, okay? We have conservation of mass, we have conservation of charge, and so on and so forth. All of those things depends on the specific properties of physical world. But this is about information, okay? The probabilities of all possibilities should add up always to be a constant. That's one, okay? You shouldn't have anything different. So this is probably the most robust conservation law, okay? Now let's check. Okay. Right. So in physics, we know that. So if we define this pxt, if you have this one, it's conserved. You should have a local conservation law, right? So you can, okay, the conservation globally, so these two conservation locally, okay. So that means so the time derivative of this one should always be related to a current, okay. So that if we do the integration, for example, so that will equals to minus okay, and this one by Gaussian's law that will equals to right, and then at the infinitum this one should be 0, okay, right? So these two actually are equivalent to each other, okay. So once you have a global conservation, you should also have this local current, okay. So what we need to do is to check this one with the Schrodinger equation. So let's check with the Schrodinger equation, okay. The time dependent Schrodinger equation, okay. So partial t, okay, pxt. Of course, you equals to partial t percent xt times percent xt, right? Okay. And this one can be done by part. Okay, and plus. And now we apply this Schrodinger equation, okay? Let me copy Schrodinger equation right here. So you have partial t percent I h bar equals to, p squared over 2m plus v over times percent, right? So that equals to minus partial square over 2m, okay, plus v r. Right, so you can put this to the right hand side. That will give us partial t, and percent equals to I h bar over I Sorry. Minus I over h bar. And the minus h bar square over 2m. This is lambda squared. So this is the general form, right? Of course, you just take the complex conjugate to both sides. So you can, yes. You can take the complex conjugate to both sides. Okay. Right. But V, of course, is a real number. So this one is just the same. Okay. So you have another equation. So anyway, you put these two together, you find that there will be two terms. So one is plus I over h bar. Okay. The complex conjugate I over h bar. And then minus right, and then times percent. And then another one is minus I over h bar. This is percent star. And what's inside is okay. And now you can see that this one is just a function times this one, right? So this one times this one times this one. Where this one times this one times this one. But there's minus sign right here. Okay. So these two will cancel each other, right? So you are left with only one term in each bracket. So that can be written as sorry. Right. Minus okay. Let's do a little bit of simplification. Okay, put these factors outside. Okay, so that will be minus. There will be I. There will be h bar. There will be 2m. Okay. What's inside is cosine right. So that's a little bit more straightforward. Okay. All right. And now you can see that I can actually do the differentiable parts. That can be written as I h bar over 2m. And then this one can be written as plus minus, sorry. Right. And then the another thing can be written similarly. But there's a minus sign right here. Okay. Right. And then you find that these two terms cancel each other. Right. But this is just a complete differential. So eventually you got a partial t p xt equals to minus I h bar over 2m. Okay. So what's inside is per psi times this differential per psi star minus per psi star times this gradient of this. Okay. It's and now this can be of course written as minus h bar of I, and then 2m is very nice. Okay. So if we compare this one to be the conservation law, okay. So you can have this current J can be written as 1/2m, you know, h bar of I d over dx per psi, or minus per psi times h bar of I d over dx per psi star. Right, so this one is very intriguing. Look at this one. This one is just acting the momentum operator on this one, right? And this one can be written as this way, right? Okay, because you can put the minus sign, you can move the minus sign from here to the compass conjugate of this. Okay, and then this one just equal to this one, right? So that's a symmetric way to write down this P. And P of m, you can interpret this as the velocity operator, right? Okay. So basically, you obtain a quite nice derivation of this current operator. So you got a J defined as 1/2m per psi compass conjugate times this one, and then plus okay. Or in other words, you can say that this is just take the real part of this one, right? So you can interpret as velocity, okay, of this this local velocity, okay, of and weighted by by this wave function, okay. Right. So this one is the current. Okay. Term, okay. And then you have partial t, pxt, and plus this one equals 0, right? According to the time-dependent Schrodinger equation, okay. Right. So this one leads to the conservation of total probability. Okay. Right. So that's you can see that there's a way to to work on this Schrodinger equation, even though you don't know too much about the specific properties. Right. So this is a nice property of this wave function. Okay. All right. Say any questions at this moment? Okay. All right. So if we move on, okay, so we can consider how to solve this Schrodinger equation. Okay. So let me write down this one once more. That's I h bar partial t per psi equals to the operator Hamiltonian acting on this one. So this is the time-dependent Schrodinger equation. Okay. Right. And more specifically, you can see that this one is partial t per psi equals to minus h bar squared over 2m d squared partial squared partial x squared plus vx per psi. So you can look at this one, the left hand side is contains only this. So only this one shows, right? On right hand side, but only this x or d over dx show up, right? So with this kind of properties, so we can have the separation of variables. Okay, so that means we can write down this per psi xt. Now factorize this one as phi x times ft. Okay, so you put this into the equation. You find that the equation becomes I h bar and the partial t and f, right? And then times phi, because this phi depends only on x, so you can move this one outside. On the right hand side, you can move this f outside. And then you have only an operator, okay, defined in x. Okay. And then you can move this one to here, and move this one to here. And then the left hand side depends, so it's independent of x, right? And the right hand side is independent of t. And so, but the two must be equal. Okay. So that means you must have both of them to be independent of x and independent of t. So that means they must be constant. Okay. Right. So you have you must have this I h bar partial t f over f equals to a constant, and this one should equals to, let me use shorthand notation, add the Hamiltonian acting on this phi, okay, over phi, right? That means you got two equations. Okay, this is the first equation. This is the second equation, and this one is very easy to solve, right? So this one, the two is easily to solve. So that's just ft just equals to e to minus I e times t over h bar, and times the constant, right? And this constant can be always solved into phi, so we don't need to consider this constant. So that's the solution, right? Okay. So that means the function will be given a E. This function will be always like something like this one. Okay. So then you got the important equation, that is what we need to do is just to solve this equation, right? So this one is called a time-independent Schrodinger equation, because the time dependence is already solved. It's just exponential oscillating factors. Okay. And immediately you can see that this one has an interpretation of energy, right? Because this oscillating factor, if we consider plane wave, this E is just h bar omega, right? So that means this one has the interpretation of energy, okay? Right? Okay. Right, so let me recap this one. The time-independent Schrodinger equation is given by okay. So this E is called the eigenenergy. Okay, so it's energy. And this percent E is called the eigenfunction of the Hamiltonian. Okay. And the time-independent Schrodinger equation now becomes solving this one is to solving the eigenvalue problem. In partial differential equation, right? Theory. Okay. So why do we call this one eigenfunction? Okay. If it's eigenfunction, that means you apply this action, this operation on the wave function. You still got the same wave function, except for constant. Right? For example, you can if you do this one twice, see what will happen. And this one, of course, equals to according to the definition, right? So that equals to this, right? Because it's an eigenfunction. And then because of a linear, so this is because this is eigenfunction. And this is a linear operator, so that means this will equals to something like this one, right? So that will equals to E times E percent E. So that will equals to E squared. So this is a very, very nice property of this eigenfunction. So that means you can apply this one once, twice, 3 times. So you just simply just multiply this eigenvalue once, twice, 3 times, and so on and so forth. Okay, so you can actually write down anything of this one. Right. So hence the name. Eigenfunction, okay? That means you, no matter how many times you apply on this one, you will not move this state to another one, okay? Right, so this is the eigenfunctions of this, okay? All right, so let's consider, we have a little bit more time, let's consider an example, okay? Consider a simple example. Free particles. So this is an easy one. It's very easy to obtain the and the eigenfunctions. Okay, so that means there's no potential. This is equal to 0. Okay, so the Hamiltonian will be simply only one term. Okay, so that is okay. Right. So let's look at the eigenfunctions of this. Okay. This means so that's a very simple differential equation, right? So the solution actually is extremely simple. So this one equals to psi x is just proportional to or any function. Let's look at a constant times e to I square root of actually let's say k x okay with this k just square times h bar squared over 2m just equal to e. Okay, so that means k equals to plus or minus square root of 2m e over h bar squared, and this k is just the wave factor. The solution is just the plane waves, right? That's very simple, okay? Right, and then the solution, so we can call this one ek, okay? And then this one is ek, okay? So this one will be just k, and just k, okay? Right, so the time dependence, of course, will be, remember, we have two factors, right? So that will be psi kx e to minus I ek t over h bar, okay? So this is e to I kx minus I ek t over h bar, okay? That's nothing but just I kx minus I omega k times t, okay? With omega k equals to ek over h bar equals to 2m ek over h bar squared and over h bar, right? So that is, sorry. Equals to h bar squared, k squared over 2m and over h bar, okay? So that is the omega k. So this is the solution. It's very simple, actually. And now let's discuss the possible values of this ek, okay? So okay. And to do this, you can say that this, first of all, this plane wave x cannot be normalized, as we have said this before, right? So that means a physical state should be a wave packet. Say something like this one, right? So it should be something like this one. And this one should have normalization. Okay. So we should form something like this one. But then you can say that to have this one, so that means this k must be real number. If it's not real number, you can say that if k is imaginary, okay, and you got something like this one. Okay, so this will goes to infinite if x goes to infinite. So that means you form a wave packet, and this wave packet will always diverge. Okay. And it cannot be normalized. Okay. So to have a normalization condition that can be formed by using different components of this K, and then you must make sure all of this one be real number, and then this energy should always be greater or equal to 0. Right. So this gives us a very important feature of this, time independent Schrödinger equation. Okay. Okay. The lesson from this free particle time independent Schrödinger equation. Okay. So the physical condition or more specifically, this psi x should not goes to infinite at x goes to infinite. Okay, and this one is kind of a boundary condition in mathematics. Okay, in maths. Okay, so it's this kind of a physical condition in physics, all the boundary conditions in maths that gives possible eigenvalues of H. Okay, so that will fix E. Okay, so not all E be possible. Right? In the case we have considered that E must be positive for free particles, right? So it is actually this kind of a boundary condition. If we talk about these things in mathematics, or the physical conditions that is constrains the possible values of the Hamiltonian. So let us have discrete or sometimes a lower bounded energy. Okay. So otherwise we will not be able to have a normalized probability distribution at all. Okay. And many people say that you cannot have negative energy. Okay. Because the energy of a particle must be positive. But that's classical physics, right? In classical physics we say that you have kinetic energy and this should always be positive, fine, okay? But in quantum mechanics, it's just an eigenvalue of a Hamiltonian. Who tells that it must be positive value, okay? And it's the physical condition that dictates that the eigenenergy must be positive, okay? Right? So for example, okay, and E should be this one for free particles. Okay, okay, and then later more examples. Well, this E equals to discrete numbers. Okay, they cannot take an absolute value. Okay. Unlike free particles, this E is a continuum. Okay, so this is a continuum. Right. But we're going to see more examples where the energy actually can be is going to be fixed as only discrete values. Okay. So that is pretty much what we have for today, okay? Let's see, are there any questions?